doing some weird stuff, but we'll forget about that. Okay, so I'm basically trying to set up all the material that you will need to understand this afternoon's tutorials. How many of you have already done DFT calculations? Okay, so pretty much everyone. So I think then everything I'll go over is very basic and fundamental, so I'll go a little fast. And I would suggest that if you need a clarification, a quick clarification, stop me, and if you have longer questions, we'll save them for the end. So my talk's in 3 parts. The first part is a review of some basic concepts from solid-state physics, and that I'll do very fast because I think everybody is familiar with this. Then I'll talk about the particular issue of Brillouin zone sampling that we use in our calculations. And then if I have time, I will go over the structure of the self-consistent loop that we use to do the DFT calculations in PWSEF. So if you're doing a calculation on a system, obviously the first thing you have to do is to specify the system. And throughout this talk, any input parameters that we need for the PWSEF code, I put them in these peach-colored boxes. And you don't have to write them down or remember them. We'll give you more material, but just to tell you, later on, if you're preparing your input files, you might want to go back and correlate with what it is. So let's first talk about crystals. So we have periodic structures that are built up out of repeating units. And every crystal structure, you divide it up into 2 parts. First, you have a Bravais lattice, which tells you the shape of the unit cell and how it repeats. And to do that, you have to give 3 primitive lattice vectors, which we call A1, A2, and A3. And then the next step for the crystal structure is that you have to say where the atoms are. And to do that, you specify an atomic basis. So this is shown schematically here. This green grid is supposed to represent points of the Bravais lattice where they intersect. These magenta arrows are the primitive lattice vectors for this case. And then you add your atomic basis, and then you get this crystal structure. Is there a pointer? Okay, so when you have a crystal structure, you have a unit cell, and let us first consider the points as representing the points of a Bravais lattice rather than atoms. So in all 3 pictures, I've drawn the 2D hexagonal lattice or triangular lattice, and I've just shown you different examples of unit cells that you can have for them. So this is perhaps the natural unit cell that you would get if you just take the parallelogram that you get with the 2 primitive lattice vectors. This is the prescription for the Wigner-Seitz primitive unit cell. We don't use it too much in real space, but in reciprocal space it's often used, so that's why I showed it. And this one is an example of a non-primitive unit cell. So this is as valid a unit cell as this one is, or this one, but it is larger than it needs to be. So in this you have 1 lattice point per cell, and here you have 2 lattice points per cell. And you could choose to work with that, and sometimes you might choose to do it even though it will be a little more expensive to do. So here in 3D, I've just shown you 2 examples. Again, very quickly, this is the conventional cubic cell for the FCC lattice, the face-centered cubic lattice. And the blue rhombohedron that I've drawn is the primitive unit cell, which only contains 1 lattice point, whereas this green cube is the conventional cubic unit cell, which has 4 points per cell. So all the crystal structures that we have in 3 dimensions can be divided into various crystal systems, and some of those systems are further subdivided into different kinds of lattices. So this picture shows the 7 3-dimensional crystal systems, and they are specified. You decide which of the crystal systems you have based on the lengths of the lattice vectors, so A1, A2, and A3, whether they're of equal length or different length, etc., and then what the angles between them are. And again, I realize I'm going fast through this, but I think everybody knows this, so this is just a quick reminder because we need it for the afternoon. And so in order to run the PWSCF code, you have to tell it which Bravais lattice you are in. So that's done with this one parameter. And then you have to tell it the information about the primitive lattice vectors, how long they are, and what angles they make with each other if necessary. And you might also choose to say, I don't want to specify any crystal system, I just want to give it the lattice vectors, and that option is also here. And once you have the Bravais lattice, you have to tell where the atoms are positioned within your unit cell. And again, it's sort of very obvious what you have to do. The first thing you have to say is how many atoms you have, then how many types of atoms, that is how many elements you have, and then where they're sitting. And just one thing I wanted to mention, because we need it in the afternoon, is that for cubic crystals, we usually specify the positions in units of the conventional cubic cell, even if we're working with the primitive unit cell. Am I going too fast? No. Okay, so that's it. And now we go to reciprocal space and wave vectors. So if you have these green dots are supposed to represent lattice vectors capital R in real space, and then you have a reciprocal lattice in reciprocal space or K space, which these purple dots represent. And one thing to remember here is that the spacing of these is inversely proportional to the spacing of these. So if you were to scale up this lattice, that is, you would have larger unit cells in real space, then you would get denser G's, reciprocal lattice vectors, in reciprocal space, which can have an impact when we're working with large unit cells. The first Brillouin zone, you can either think of it as, usually it's drawn, it's again a primitive unit cell in reciprocal space. You can use the Wigner-Seitz cell, and that's what's done conventionally, or very often you look at the parallelepiped that's defined by the 3 primitive reciprocal lattice vectors. And this shows a picture of the primitive, of the first Brillouin zone for an FCC lattice. And the irreducible Brillouin zone is the smallest wedge of the first Brillouin zone that you work with, so that any wave vector in the first Brillouin zone can be obtained from one in the primitive, in the irreducible part by performing symmetry operations. So, for example, this is again the first Brillouin zone for the FCC lattice, and this magenta wedge over here is the irreducible Brillouin zone. And we talked about electrons in a periodic potential. This also Stefano Baroni mentioned. If you have electrons in a periodic potential, so that this means that if you add a capital R, that's a lattice vector, to any position, you have the same value of the potential. And then by Bloch's theorem, you can say that the wave function will have this form. It will be a plane wave multiplied or modulated by a periodic function. So this function u has the periodicity of the lattice. And one can choose to expand. So since this u, that is the periodic part of the wave function, has the periodicity of the lattice, when you make a Fourier series expansion of it, you only have the reciprocal lattice vectors G appearing in that expansion. And so you substitute this into the block form of the equation, and you can see that you can expand the wave function as some coefficients multiplied by plane waves of the form e raised to I k plus g dot r. And these k plus g's we can draw as a grid in k space. Again, I've drawn it in 2D just for simplicity. Now, it's only true for periodic systems that this is a discrete grid. Okay, so if you want to work with plane waves, you really need to work with periodic systems. And however, you still need an infinite number of plane waves in this expansion. And in practice, what we do, however, is we truncate this. So we say that the contribution from higher Fourier components is small, so we truncate this expansion. So this is a schematic diagram of how you truncate that expansion. So you say that if the modulus of the wave vector is less than or equal to some value, you keep it. Otherwise, you throw it away from your expansion. And by convention, this is done in energy units. So you say that h bar squared k plus g squared over 2m, where m is the mass of the electron, should be less than or equal to E cut. So this is an equation of a sphere. Okay? And so what you do is you draw such a sphere in reciprocal space, and then you keep all the k plus g's that fall inside this sphere. Okay? And now comes the point that I mentioned before, which is if you have a very large unit cell in real space, then you'll have a very dense mesh of these magenta points in reciprocal space, and so you will have a lot of plane waves falling inside your cutoff, which will make your calculation more expensive. And there's an input parameter that you have to give your PWSEF code, which tells you what that plane wave cutoff is. And this also, Stefano briefly mentioned that you can work with periodic boundary conditions, which are called the Born-von-Karman boundary conditions. And so what you do is that if you have a crystal with some primitive lattice vectors A1, A2, and A3, then you apply periodic conditions, boundary conditions, using a supercell, that is something that's larger than your primitive unit cell, by scaling up by a factor of n1, n2, and n3 along your three primitive lattice vectors. And then you can use Bloch's theorem. This is shown, for example, in Ashcroft and Mermin. And you'll find that you only have certain allowed values of wave vector k, which are given by this form. And if you examine this, you will see that the number of allowed wave vectors you have in the first Brinmer zone is equal to the number of unit cells in your crystals. So it's determined by the size of the supercell that you have chosen. Band structures are graphs that show the electronic eigenvalues En versus wave vector k. Now, of course, k is in a three-dimensional space, so by convention, so you want to, for example, show what it looks like in this whole first Brinmer zone for an FCC lattice. You take cuts along different directions, which is what's been done here. So the colors here correspond to various points over there. And then you draw the energy versus wave vector, and you get, for example, the graphs that look like these. And the important thing is whether or not the Fermi level falls within a band of allowed energies or not. And for aluminium, you can see that you have partially filled bands because the Fermi level is falling in the middle of a band, and that's why it's a metal. Whereas if you have a semiconductor or an insulator like silicon or diamond, you can see that the Fermi level is falling within a band of energies that isn't allowed. And this has some implications for us in how we do our DFT calculation. When you calculate the band structure in practice, of course, what you do is you discretize your K space, and so you calculate the energies at some discrete values of K. come back to that in a minute. And then you have something called the density of states, which tells you how many allowed states fall within an energy interval. So this is, for example, for aluminium, this is the density of states versus energy. I've drawn it sideways, that is, it's rotated by 90 degrees so that the density of states is your y-axis and the energy is your x-axis. The reason I did this was so that you could see that there is, if you sort of integrate out the information from all the directions in the Brillouin zone contained in the band structure plot, you get the density of states, and you get these very sharp features, sometimes called the Van Hove singularities. And if you need to get them right, you have to do a very careful job. And so I'm just showing you some examples here. This is calculating the density of states in practice, because that's something we will do this afternoon. So the density of states is defined as a sum of delta functions. Okay, now there are two things that we have to approximate here. One is this is actually an infinite sum. It's an integral over all wave vectors in the Brillouin zone. So we will approximate that integral by discrete sums. So we have to do that carefully. And the other thing is, of course, we have to approximate the delta function, which is infinitely sharply peaked as a somewhat spread out quantity. So here, I'm just showing you some examples of densities of states for bulk rhodium. In these three, the student used the same wave vector mesh, which is 8 by 8 by 8 wave vectors in the first Brillouin zone. But he used different widths of the Gaussian. And so if you used a very small width, you can see that it looks like a bunch of sharp peaks, which isn't representative of what the true situation is. If you spread it out a little bit, it begins to look like a reasonable density of states. However, if you spread it out too much, then you will lose all the important features. So this is something we will, again, see this afternoon. And here is the other side of it. What happens if in this sum you take too few wave vectors? So here in these three, the broadening of the delta function into a Gaussian is kept fixed in all three graphs, but the number of k points at which we have sampled the energies is different. And you can see here that if you have too few k points, it doesn't look okay, and then you have to build up to a reasonable number of k points before you get a reasonable density of states. And if you want to do, you could say, well, I want to sample just at a discrete grid, but I want to do some interpolation between these. And there are methods that you can do this, that allow you to do this. And for example, in our code, you have the option of doing this with the linear tetrahedron method, where you take a grid of k points and you break up the in-between region into tetrahedra, and then you do an interpolation within these tetrahedra. And this, for example, would be a good thing to do if you want to get fine features like the Van Hove singularities correctly. And in this part, the last thing I wanted to say is what happens. I said the system has to be periodic if your grid of g's or k plus g's has to be discrete. But of course, sometimes you want to do a calculation on a system that is not periodic. So here are some examples of non-periodic systems you might want to calculate. For example, here's a surface. So these yellow circles are bulk atoms, and over here you have a surface and no more atoms over here. So you have lost periodicity in this case in one direction. You might lose periodicity in two directions, so you only have periodicity in one direction, for example, if you have a nanowire, or you might lose it in all three directions, for example, if you have a cluster or a molecule, or you could have, in a crystal, you could have an impurity atom sitting there, or a vacancy or something, and all of these are things that destroy periodicity. So what do we do if that's the case? we work with artificially periodic supercells. This is again something that Stefano briefly mentioned in his talk. So for example, for this surface case, what you do is you say, okay, I'm going to represent my system as a slab, and then a vacuum, and then again the slab, etc. So this is an artificially periodic system, and the unit cell for this system is drawn in magenta over here. And of course, you have to do this carefully, as was mentioned in the previous talk also. So if you don't have enough layers here, then you'll have these surface atoms interacting with these, which you don't want. And similarly, you may have interactions across the vacuum region if that isn't thick enough. And then similarly, you can do it for a cluster, etc. So I think we won't do any such systems today, but in tomorrow's tutorial, you will do some systems where you have to introduce artificial periodicity. Okay, so that's the first part of my talk. And now we come to the second part, which is Brillouin zone sampling. So how do you select the K points that you sample? And the part of the input file that this concerns is called the K points. So in order to calculate many quantities, such as the total energy or the charge density, etc., we have to integrate over the entire Brillouin zone. So there's some property that we can call P, and to evaluate it, you have to integrate over all the wave vectors K in the Brillouin zone, and then you also have a sum over the occupied bands. So here N is a band index. Now, in principle, to get the exact value, you need this to be an integral over all the K's in the first Brillouin zone, so it's an infinite number of wave vectors. But in practice, we instead sample over a finite number of K's, and that is called Brillouin zone sampling. So instead of the integral that you had in the previous equation, now you have a sum over certain wave vectors in the Brillouin zone. Now, for computational reasons, obviously you want this number of wave vectors to be small. And the number that you actually need to get a good converged result varies from system to system. It depends on the kind of band structure that you have. And therefore, in any calculation, this is very important to test your convergence with respect to K-point sampling. And that is, again, something we will do in the tutorial this afternoon. Now, the first thing we can do to reduce the number of Ks is to use the irreducible Brillouin zone instead of the whole Brillouin zone. So here is the same picture that I had shown you a few minutes back. This is the first Brillouin zone for an FCC crystal, and these lines in magenta show you a wedge, which is 1/48th of the whole Brillouin zone. Now, by symmetry, you can say that if you know the value of some quantity on any part, any K vector that falls within this wedge, you can determine its value in the whole Brillouin zone. Okay, so if it is something, for some things like eigenvalues, it's just the same in all its images, if you like. But for other quantities, you have to do some symmetry transformations, like for the eigenvectors. Now, within this wedge, not all points have to be counted the same number of times. So, for example, this point here is the zone center, and you have to only count this once, because if you take its sort of images in the other equivalent parts of the Brillouin zone, you get the same point back. So you really should count it only once. However, if you have some generic point that falls in the interior of this wedge, then you really need to count it 48 times, because there are 47 other equivalent points in the entire Brimmer zone. Some points which have high symmetry, you do not, however, need to count 48 times. For example, the L point, which is along the 111 direction and on the surface of the first Brimmer zone, you have to count that 8 times, etc. Okay, so also the X point, for example, you would count 6 times. Yeah, 6 times. So to account for this, what you do is you first, this sum that you had, you replace the sum that you had over the entire Brimmer zone by a sum over just the irreducible Brimmer zone, and then you add these weighting factors which depend on how symmetrically oriented the position of that K is. Okay, so the weight depends on, it varies from point to point, and then you have now already reduced your computational cost considerably by going from the full Brimmer zone to the first Brimmer zone only. And then you still want to use as few K points as possible. So are there clever ways of choosing them so that you can get away with using very few K points? So this was an especially important question, I would say, in the early days of our field, when computers weren't very fast, and if you just couldn't afford to do a lot of K points. And so the extreme approximation you can make is to say, can we just take 1 point, we evaluate the quantity of just one wave vector, and then say that from this you can get an approximation to its value over the entire Brimmer zone. So this was suggested by Baldareschi. It was called the mean value point. For various crystal structures, he said which single point would be the best approximation. And then a further development on that idea is that you could have a few what are called special K points, which give you a good approximation to the final value. So the most common ones are those that were listed by Chaddy and Cohen, but there are also other ones, for example, by Cunningham. And so this shows the Cunningham points for a 2D hexagonal lattice. So this hexagon here is the first Brimmer zone chosen according to the Wigner-Seitz prescription, and this rhombus shows it using just the parallelogram given by the two primitive lattice vectors. So the crosses, or alternatively these circles here, are a choice of K points that you can make to get fairly quick convergence. But nowadays this isn't as much of an issue because we do have faster computers and we can afford to use more K points. And so nearly always what we use are called the Monkhorst-Pack K points. And here you do something which seems very intuitive and natural to do. You just have a uniformly spaced grid of NK1 times NK2 times NK3 points in the first Brimmer zone. So for example, this is again the hexagonal lattice. These two vectors B1 and B2 are the primitive lattice vectors in reciprocal space. And in the first case, you divide them into 3. So you have 3 divisions here and 3 divisions here. And so these 9 K points are the Monkhorst-Pack mesh that corresponds to a choice of 3 by 3. Similarly here, instead you've chosen 4 by 4. What I've shown over here is the way that the PWSCF code, which is in Quantum Espresso, chooses the Monkhorst-Pack K points. So just to avoid any confusion, I want to mention that this is somewhat different from what was done in the original Monkhorst-Pack paper, where if you had an odd grid, it was centered on the zone center at this point, that is k equals 0, also called gamma. And in their paper, if you had an even grid, this was not true. It was shifted away from the zone center. But in PWSEF, regardless of whether the divisions are odd or even, it's always centered at gamma. But you can choose to shift it away. Okay. So for example, over here, I show for the 4x4 case, this is the unshifted grid where it is centered at gamma. And this is the shifted grid where you have translated the whole grid to the center of this rhombus. Okay? So this is the shifted grid, and how you tell the code is you tell it NK1, NK2, NK3, which are the grid divisions along your three primitive reciprocal lattice vectors, and then K1, K2, K3. If they are 0, you don't shift them, and if they're 1, you shift them. Okay? And it can often be favorable to shift your grid. You can frequently get comparable accuracy with fewer k points in the irreducible Brillouin zone, but you do have to be a little bit careful because for some crystal systems, the shifted grid does not have the full symmetry of your crystal. So how do you choose grid divisions? Again, this is done in a very natural and intuitive way. So you space the grid in a way approximately commensurate with the length of the B's. The B's are the primitive reciprocal lattice vectors. And of course, you have to remember that dimensions in reciprocal space are the inverse of dimensions in real space. So for example, if you had a square first Brillouin zone for a 2D square lattice, then you would say that, okay, supposing you've decided that you want to do a 4x4 sampling in reciprocal space. Now, if you have a cell in real space that is twice as long along the y direction, that means that in reciprocal space, your first Brillouin zone is half as long in the y direction. Okay, and therefore, you do not need to use 4x4 now. You can use 4x2. Okay, and sometimes, of course, you may have different unit cells where you can't get exactly commensurate divisions. So supposing you've extended your cell by a factor of √3, for example, okay, then you just do approximately. This is just a rule of thumb, if you like. And for the cases where we have made an artificially periodic supercell, then along those directions where you've introduced this artificial periodicity, you should have only one grid division. Okay, because it doesn't really have any meaning to say you have a periodic system and k values in that direction. So for example, here, this is the surface case, and along this direction we have introduced vacuum region to make it artificially periodic. And so in your reciprocal space, you should just have one grid division along that KZ direction, KZ, sorry. Now, there is a sort of reciprocal relation between supercells and Brillouin zone sampling. So if you were to increase the supercell in real space by some factor Ni along the AI primitive lattice vector, you could get exactly the same results by instead reducing the number of divisions in the new smaller Brillouin zone by a factor of Ni. So here, for example, again, here's a 2D square lattice. This is you have chosen the primitive unit cell, and for which you have a square first Brillouin zone, and say you have chosen to do a 4x4 mesh here. Now here, instead of making the choice of the primitive unit cell, you have chosen to make the cell twice as long along the x direction. Then if you therefore halve your k sampling in the kx direction, then to the limits of machine accuracy, you get exactly the same results. So one can see why that is so here. I have taken just a very simple free electron-like band, so it looks like a parabola. And the dashed line is the value that we have using the primitive unit cell. And you're sampling it at 4 k vectors, so you're sampling it here, 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 and here, these 3 green circles. Now, if instead you make this choice for the unit cell in real space, and therefore this choice for the Brillouin zone in reciprocal space, now this red lines are the limit of your first Brillouin zone in this case. And instead of having just one band, you see 2 bands. Okay, and they've been folded, and you will sample at these 4 yellow crosses, but you can see that you would get exactly the same answer as you would in the previous case. So this is something that we will do in the tutorial again this afternoon, and something for you to think about is which choice would be better, and are there any circumstances in which one choice would be better and circumstances in which the other would be better. So to specify k points in PWSEF, again I'm just showing this to you. You don't have to write it down, you don't have to remember it. We'll give you the documentation again this afternoon. So you first tell it whether it is you give one of these 4 options. So if you say gamma, that means you use only the zone center, k equals 0. And it's important to note that if you're going to do that, it's better to just say gamma in words rather than just say 111 or something. Because if you have k equals 0, then your wave functions can be chosen to be real, and then you can use different routines in your code which are faster. Okay? If you say automatic, that means the code will generate a Monkhorst-Pack mesh. And if you're choosing that, then you also have to specify NK1, NK2, NK3, which are the grid divisions, and K1, K2, K3, which are information about whether to shift or not. TPIBA stands for 2 pi by A. And if you do that, it means that the K points are specified in units of 2 pi by A, where A is the lattice constant. And then NKS you have to supply, which is the number of special K points whose values you supply. And then you have to give the coordinates of those special K points and their weights. So this is if you are going to specify K points rather than having the code automatically choose Monkhorst-Pack K points. And if you're specifying them, you could also choose to specify them in units of the primitive lattice vectors rather than in Cartesian coordinates. So you have to look, when you're running a code, you have to check that you're converged with respect to your choice of K points. So here is an example. This was one of my students just ran it. So she took carbon in the diamond structure, and this is the total energy as a function of the number of divisions she chose in her K-point mesh. And you can see that here it looks like it's converging, but the scale is a bit difficult to see, so she blew it up here. And you can see that it seems to be converging, but notice that the convergence is not monotonic. And so you have to decide how accurately you want to know your energies, and then accordingly decide that this is the value of your K-point mesh that you're going to use. And in this case, I've plotted the total energy, but it's worth keeping in mind that most of the time you're interested in differences in energy. Okay, for example, you might be interested in the say if you're interested in absorption energy, then you have the same surface slab with the molecule adsorbed on it and without. and you're interested in the difference between those two energies. And if you're doing exactly the same k-point sampling and the same unit cells for the two calculations, then you can hope that there will be some cancellation of errors when you subtract one from the other. And so you might be able to get away with using a somewhat coarser k-mesh. This is again examples from a paper of ours where we calculated the absorption energy for CO on the iridium 100 surface. In this case, we plotted not NK1 or NK2 or NK3, but 1 over NK, where that's the total number of K points. So you would say that when this is 0, that's when you would expect to get your converged result. And you can see that we're slowly converging to it. And the dashed line was with the Brillouin zone center, that is unshifted K-point mesh, and this one is a shifted mesh, and you can see that this one seems to converge somewhat faster. Okay, so now there are some special issues for metals. So everything I've talked about so far is very general, but now let's consider what happens when you have a metal. So this is the same equation that I had before. That is, to get the average value of some property P, I have to integrate over the Brillouin zone. Okay. Now for metals, okay, so and we're only looking at the occupied state. Now for metals, because of the presence of a Fermi surface, that means for the highest band, this is not an integral over the entire Brillouin zone. It's an integral only within the Fermi surface. So here I have drawn as an example, this is copper. You can see the first Brillouin zone, and then the yellow surface is the Fermi surface of copper. Okay. Now, because of this, you have a sharp discontinuity in K space. Okay. Within the Fermi surface, it's occupied, you cross it, and it's empty. Now, anytime you want to integrate over a very sharp feature, you have to do it carefully. You need very fine K meshes to get that correctly. Okay? So, this means that if you want to get the properties correctly for a metal, you need to have a very, very fine K mesh. And that is, of course, computationally expensive. And you would like to avoid that if you can. Another issue that you can have for metals is that your loop, which we haven't yet discussed, may not converge very fast. And this is because you may have, for example, some state that lies just below the Fermi energy and another one that's just above. And from iteration to iteration, they may cross, as a result of which your wave function and your charge density will look very different in the two cases, because it's different states that are included, and then your loop won't converge. So, what is the solution? You do something called smearing. And so, we want to approximate this very sharp function by a smooth function, and we do that using smearing. Now, when you smear, you will converge faster with respect to the number of K points, but not necessarily to the right answer. And the larger the smearing, the quicker the convergence with respect to K points, but the greater the error introduced. And there are different techniques, so I will mention them briefly now. So the first sort of most intuitive thing to do is to use what is called Fermi-Dirac smearing. So here, this is an example. I've drawn some density of states. Okay, and this dashed line here is the Fermi level. So if I wanted to, for example, count how many electrons I have, I would integrate up to the Fermi level, and this is a very sharp feature. So unless I have a very fine mesh along this direction, I will get a wrong answer. However, once you go to a finite temperature, then, okay, so the number of electrons you have, you always get by taking the density states and then multiplying it by the Fermi-Dirac distribution, right? So here, the Fermi-Dirac, at t equals 0, the Fermi-Dirac distribution is a step function, and so you have this sharp feature. However, if you go to a higher temperature, then your Fermi-Dirac distribution is no longer a step function, it gets smoothened out. And so now you will see something that looks like this. Okay? So what you would like to do is to say, instead of occupying the electrons in this metal according to the Fermi-Dirac distribution at temperature T equals 0, you occupy it according to a Fermi-Dirac distribution, which is written here, with some width sigma, where sigma is related to Boltzmann constant times temperature. Okay? And again, I want to emphasize that this is not necessarily a physical electronic temperature. This is just a fictitious temperature that we are introducing in order to make our calculation converge faster. Okay? So now, so in the previous talk, you saw that you have this energy functional, which is variational. So when you minimize it, you have the correct energy. That was okay at 0 temperature. When you're at finite temperature, what is variational is the free energy, which is given by E minus Ts, where S has this form. Okay? And what we actually want is the value of the energy in the limit that sigma, the smearing width, goes to 0. And one can show that you can get this by taking half of the free energy plus the internal energy, and this will have some deviation from the correct answer of the order of T cubed, where T is the smearing temperature that you have used. However, it turns out that that's not very good. I mean, it isn't very accurate. You'd like to do a better job than that. So the next thing that people tried is what's called Gaussian smearing. So what is the idea of this? You have a Fermi-Dirac distribution, which is a step function. Now, how can you get a step function? You can get it by integrating over a delta function. That's fine? Okay, I mean with some sign differences, etc. So the delta function is very sharp, and so your step function is very sharp. But you could approximate the delta function by something that is not so sharp, and then your step function would also get smeared out a little bit. So, for example, you could try a Gaussian or a Lorentzian or something for the delta function. So over here, this is I've written the formula that you would get if you replace the delta function by a Gaussian and then integrate it, you would get an error function. Okay. Now again, you have some sigma here, where the sigma is related to the width of the Gaussian that you use. Now, you have done something analogous to introducing a finite temperature with Fermi-Dirac broadening. So just as in that case, you had not the internal energy being variational, but the free energy. Now you have some generalized free energy, which is the quantity that's variational with respect to wave functions and occupation numbers. And depending on the form of broadening that you introduce, you can work out what is the formula for the generalized entropy that you now have. Okay? Now, so if you do Gaussian smearing, it converges faster than Fermi-Dirac, but you still have errors which you would like to minimize, so there are even more sophisticated schemes. Before I come to them, I'm just showing you what I mean. So here is the total energy as a function of the number of points in your K mesh at 3 different values of smearing. So this is the least smeared, this is more smeared, this is more smeared. Now, this is our best approximation to the true correct answer, okay? I mean, it's probably slightly shifted still, but But notice that here you need a lot more K points before you converge to that value. Now over here, you have a broader smearing, and so you're converging faster, but you're converging to the wrong value. So you would like to improve it further so that you converge fast, but to the right value. So there are better smearing functions that one can use. These are, again, you can think of them as different ways of approximating a delta function and therefore integrating to get the occupation. So there's a scheme, but I'm not going through the details, but I've given you the references here. There's a scheme by Metfessel and Paxton, which converges faster than Gaussian smearing. And then there's a scheme by Marzari and Vanderbilt. Now, in this case, it turns out that you can end up with negative occupation numbers, which is kind of undesirable. So this has sort of comparable speed of convergence, but you don't have negative occupancies. And of course, you should use this, and I'm saying this not only because one of the authors is the organizer of the school and the other author is my PhD advisor. Okay, so here is a graph that shows the convergence. It's comparing, in this case, Gaussian. This is the same graph that I showed you. And this is Metfessel-Paxton. Okay, and again, the same three smearing widths. So the black is the least smeared, and the blue is the most smeared. And you can see that this one is converging much faster than this one to the right answer. Okay? And these two graphs are on slightly different scales. So in fact, it converges even better than it looks like it does over here. And just one other picture, I mean, just reversing the axis. So this is again total energy. This is 0 is supposed to be the correct answer. This is as a function of smearing width, and this is the Gaussian, and this is the Marzari-Vanderbilt. Okay, so so the point is again that you want to use a large smearing width because you get faster convergence with respect to number of K points, but you don't want to pay too much of a price in accuracy by using the larger smearing. So over here you can see that in the Marzari-Vanderbilt you can get away with using a bigger smearing compared to the Gaussian. And to smear in quantum espresso, again we will do that in this afternoon's tutorial. You have to tell it that you're going to smear the occupations. You have to say which kind of smearing you want, and then the smearing width. Okay? Okay, so the last thing I wanted to do is to go over the self-consistent loop, because that is something that we will use this afternoon. We have already done different parts of it in my talk and in Stefano's talk, but let's just go over it once so that it's clear what we'll be doing when we run the code this afternoon. So here again is the Kohn-Sham equations that we want to solve. Okay, I've used atomic units, so that's why you don't see H bars and E's, etc. So you have a Hamiltonian acting on a wave function, okay, and then you want to solve for the eigenvalue and the wave function. And of course, you have to do it self-consistently, as was mentioned in the previous talk also, because the Hamiltonian that you have depends on the solution, because if you have to know the wave functions to get the density, and then the Hamiltonian depends on the density. So you have to use some self-consistent procedure to solve this. And here is a schematic of the loop we use. So we have some knowledge of the ionic or nuclear potential, which is the external potential in our case. Then you have an initial guess for the charge density. Then you calculate the Hartree and exchange correlation potentials. Once you've done that, you assemble your effective potential. Then you actually solve the Kohn-Sham equation, so that's your diagonalization step. Once you have that, you calculate your new density. You compare your new density with whatever you had before and decide whether you have achieved self-consistency or not. If you have, you're ended. If you don't, then you keep repeating this loop until you converge. So I'll walk you through this loop rather fast. So the first thing you have to do is to tell your code what your nuclear potential is. In our case, we use a pseudo potential. So you have to tell it which pseudo potential to use. And the way you do it in Quantum Espresso is, in today's exercise, we've actually written input files which contains the name of the pseudo potential. But in general, what you would do is you would go to the Quantum Espresso web page. You would click here on pseudo. When you do that, you will get a periodic table. You click on the element whose pseudo potential you want. For example, supposing you want oxygen, you click on oxygen. Then you will get a list of lots of available pseudo potentials for oxygen. And the name of the pseudo potential tells you two things. It will tell you what kind of exchange correlation you are using. So in the case of Quantum Espresso, the place where you specify which approximation to use for the exchange correlation functional is in the pseudo potential. So it could be LDA or GGA or whatever. Okay? So for example, here this pseudo potential for oxygen is called O for oxygen, PBE for Perdue-Berg-Ernzerhof, which is a kind of GGA. And then this RRKJUS stands for Ray Brab Kaxiras Janopoulos, which is a kind of soft pseudo potential, which was then converted to an ultra soft pseudo potential. And then in your input file, you would have, for example, supposing you're doing barium titanate, in your atomic species, you have to say, okay, you have barium, titanium, and oxygen. These are the atomic masses, and these are the names of the pseudo potentials that you're going to use for them. It's important to remember that your plane wave cutoff for the wave functions, and you also have a cutoff for your charge density, which for non-conserving pseudo potentials, you leave it at its default value, which is 4 times the cutoff for the wave functions. But if you're using an ultra-soft pseudo potential, you should remember to change it. And this is because ultra-soft pseudo potentials, you have to carry around this augmentation charge for the core region because it's not non-conserving. If you know what I'm talking about, it's going to be obvious, and if you don't, it's going to make no sense at all. But just ask me afterwards, because I do want to try and finish in 10 minutes, if possible. So in those cases, you have to use a higher value for this E-cut rho. It should be roughly 8 to 12, and you have to check convergence with respect to both those quantities. In today's exercises, we will only use non-conserving pseudo potentials. So we will only do convergence tests with respect to E-cut WFC. But in general, if you're using an ultra-soft pseudo potential, you also have to check for convergence with respect to this E-cut rho. Okay, supposing you screw up and you use 2 pseudo potentials that are not compatible. For example, here for iron and cobalt, you used PZ, which is Perdue-Zunga, a kind of LDA, and PBE, which is the GGA for the 2. Then if you do that, the code is smart enough that it will complain and stop. It says error, inconsistent DFT, right, and stop it. Okay, then you have to make an initial guess for the starting wave functions or the starting density. And here, I mean, obviously, if you have some knowledge of what your final solution is going to be like, then you can use that as your starting guess. Otherwise, there are sort of standard options like a superposition of atomic orbitals. So you have some choices. You can specify if you want to for what the starting wave function is. Then you have to assemble your effective potential. I'm not going to say much about this, and some of the formulae involving reciprocal space, etc., you saw in the previous lecture. Now this diagonalization step is the really expensive step usually. Okay, so it's we have expressed a Hamiltonian in a basis of plane waves, and so you have a matrix whose size